The question as to whether light is a wave or that light is a set of particles has been debated long and very passionately in physics. One of the towers of modern physics, that is Isaac Newton, believed that light was a cascade of tiny parcels of light that he called corpuscles. So, under this corpuscular theory of light, he believed that light was a huge number of particles which were coming from objects emitting light. And when light reflected off a surface, what we were seeing was these corpuscles of light, these tiny parcels of light bouncing off the surface, much as a rubber ball bounces off a wall. On the other hand, another physicist named Christian Huygens had advanced the wave theory of light. He believed that light was a wave phenomenon. And he was able to demonstrate with various theoretical models how light would work as a wave. Now, given that Newton had a lot of sway in physics, and justifiably so, for a long time his theory had prominence. However, once the phenomenon of interference and the phenomenon of diffraction were discovered, and it was shown that light also undergoes these effects, the wave theory of light began to gain more prominence and more importance among physicists. But the question again got thrown open due to the photoelectric emission experiments, because they were giving us results that did not make sense in the wave theory or the wave model of light. Let's try to understand what were the problems that were being caused if we believed that light was a wave in these experiments. So let's say that we have a metal surface, and on this metal surface I have incident a ray of light. So we have red light, and we consider this to be a set of waves coming from some source which is hitting this surface of the metal, and some part of it gets reflected and some part of it is absorbed into the surface of the metal. If we assume that light is a wave, then we understand that a wave is a continuous phenomenon. It is spread out in space and it is a continuous phenomenon. The incoming light energy will have some level everywhere as it travels through a medium. And this energy is being emitted continuously, and it is also being absorbed continuously by the metal surface. If this theory was true, and the energy was being emitted by the source continuously and was being absorbed by the metal continuously, it would stand to reason that when we see the emission of electrons from this surface, what we call photoemission or photoelectric emission, it would stand to reason that these electrons were also gaining this energy continuously. If that was true, then the number of electrons which was being released would be independent of the wavelength of light being used. We would be seeing photoelectric emission for any wavelength or any frequency of light, since the gain of energy by the electron was a continuous process. But the photoelectric experiment clearly showed this is not the case. What it showed was that there was a particular wavelength of light beyond which the emission would not take place. For example, let's say we have a metal X. It was seen that metal X would have photoelectric emission only if light of blue wavelengths or less than that were used. Or in other words, lights of frequency equivalent to the blue light or greater than that were used. There was no photoelectric emission if you were using a longer wavelength or if you were using a lower frequency. And this was one of the biggest issues with the wave theory of light with regards to the photoelectric emission experiments. This was a very difficult thing to reconcile with the existing idea that light is a wave. The other problem was that the energy of a wave is a function of its amplitude. So if I have two light sources, let's say that we have a source of blue light and we have a source of red light, and they are sending out waves of blue and red light in all directions. So here we have the emission of red and blue light in all directions. Now, to my eye and hopefully to your eye, the brightness of both of these sources is the same. So that means that the energy of this light wave is not really depending on its color, because both of them have the same brightness. If light is a wave, the brightness or the amount of energy in the wave depends on the amplitude of the wave. But again, we saw from the photoelectric experiments that it seemed that light of a higher frequency, for example, blue light, intrinsically was producing higher energy photoelectrons compared to light of red color. This meant that there was something very, very wrong with the way we had conceptualized how light behaves in its interaction with matter, because neither of these results could be reconciled with the wave image of light. It again seemed that the particle picture of light was the correct one. So we are going to understand how breakthroughs were made in our understanding of the true nature of light, and how we were able to put a mathematical underpinning to our understanding of how light behaves.
Manorama Horizon. Learning made simple.